Hello and welcome to the Performance Summit talk entitled Why Do Programs Get Slower Over Time? My name is Ivica Bogosavljevic. I am a C and C++ performance specialist. My professional focus is application performance improvements. That means techniques how to make your C++ program run faster, either by using better algorithms, better exploiting the underlying hardware, and better using the standard library, programming language, and the operating system. I work as a performance consultant. That means that I help developer teams deliver faster software, and also I write for a software performance blog called Johnny's Software Lab. There is a link here down in the footer. So if you have any problems with C++ software performance, you can write me using this email address. Okay, so let's get started. Now, the effect that I guess most of you have already experienced is that you have a program that runs at acceptable speed at one moment. Now, after some times, for example, 6 months, it's slow, but nothing changed spectacularly. Why is the reason for this slowness, and can it be fixed? Now, let's first set the baseline expectations for performance. The program's performance doesn't change when we add new features. So new feature, you don't expect that the new features will actually make programs slower. The second expectation is that the program's runtime grows linearly to the dataset size. So if the program is processing n pieces of data, and at some point you increase the amount of data processing, let's say 2 times n, then the programs would be at most 2 times slower and not more than that. So in this talk we cover why do programs get slower when new features are added, and why do programs get slower when the data size grows. Okay, so let's start. The first line of problem is related to the architectural issues. Architectural issues happen when software hasn't been designed with performance in mind. Now, these kind of performance issues can be quite nasty to fix, because they can require large rewrites, and they can also break existing APIs. So one of the architectural issues that happens often is called chatty components. When it comes to performance, component API should have the following properties. It should strive to minimize the number of times component A has to talk to component B. It also strives to minimize the amount of data exchange between components A and component B. So what happens is that these are the ultimate goals if you strive for performance sensitive programming. Now, there are some components that talk a lot that we call chatty. So this happens often when your component is processing data by one instead of processing data in bulks or batches. Now, what are the problems with chatty components? First, there is the overhead of function calls. Then there are missed compiler optimizations, because compiler optimization require locality, and when the components are chatting, there is no locality in the sense that code locality, so the compiler optimizations get mixed. Also, when the components are chatting, there is also overhead of mutexes if the components are thread safe. And finally, there is a communication latency. Now, communication latency is not typically a problem when you're running in a single process, but if you're running in multiple processes or you're sending data over network, the communication latency can be huge. Now we have an example of malloc and free. Malloc and free are in C and C++ libraries, standard library, they're used to allocate and free allocate memory from the system and return the memory back to the system. Now what happens is, imagine a situation when you have to allocate 1 million identical blocks of small identical blocks. That means that you will have 1 million calls to malloc. Now, if malloc is thread protected, mutex protected, that means you will have 1 million call to mutex lock and 1 million calls to mutex unlock. The one problem is that another problem is that with this kind of system design, malloc, the component that implements malloc of free, doesn't know how much memory should it ask in advance. So it can, because you can organize memory a bit differently if you know that your program will be asking 1 million, will be doing 1 million calls to malloc. So malloc and free are one example of simple API that is effectively performance ineffective because it incurs too much overhead. Another architectural issue that happens a lot revolves around data copying and data conversions. So data copying and data conversions, they don't do any actual useful work. Data copying just moves data from one place to another. And data conversion converts the data from the input memory representation to a different memory representation, but without essentially modifying or doing any processing on the data. So you can imagine data conversion when you're just converting from one class representation to another without actually doing any useful processing. Now, as more components are added to the system, this increases the likelihood that your program will have to do some kind of data copying or data conversions. Now, with careful API design, you can avoid unnecessary work. So first, you need to agree in advance about the data layout before you design your APIs. You don't want incompatible data between APIs because this will require data conversions. Also, when you need to carefully plan what component allocates data buffers in order to avoid unnecessary data copying as much as possible. Now, the third thing that's also very common is called contention. So the meaning of the word contention means getting stuck in line and waiting for something to happen. Now, in the world of components, happens when a component is oversubscribed. What does that mean? It means that a component is doing a lot of processing simultaneously, and the other component that try to access the component are either waiting on a mutex or they're waiting on a network socket. Now, a software thread can get stuck waiting on a resource. So if you have several threads in your program, one thread can wait for another thread to finish something. In the case of contention, or in the case of oversubscription, the waiting times actually explode. So what happens? So here's an example. The formula that gives the rate, the function between waiting time and component utilization is called the Kingman's formula, and it is used everywhere, not only in software development. So what happened is that if utilization is low, let's say less than 85%, then the waiting times are reasonable. So the waiting time here is given in minute, but you can think of it waiting time in milliseconds or microseconds. But when the utilization of any resource grows to 95 or close to 100%, then the waiting time just explodes. This is an exponential function, and at 100% it's endless. It is infinite. The waiting time is infinite. Now, example of a component that can have this problem is a logger. So a logger is a component in every medium to large system that's used to output debug data to files. Now, logger is typically shared among several components, and if this is the case, then you need to have a mutex that prevents that several threads are accessing the logger simultaneously. Now, what happens is that with the logger, if many components are trying to access the logger at the same time, the logger can become oversubscribed, and you will see that the runtime, the waiting time explode, and the system becomes really slow and unresponsive. So this is what happens with the logger. Okay, these were all architectural issues. Now, another type of issues are called algorithmic issues. What happens with algorithmic issues? So if you have a large enough data set, the algorithms that dominate the runtimes are the ones with a high algorithmic complexity. So if you have your program consists of some loops, several of them, and each of them has its own algorithmic complexity. Now, if the data set is really large, only the loop with the highest algorithmic complexity will dominate the runtime. So, for example, if the highest algorithmic complexity loop in your code is of n3, then this loop will dominate the runtime when the data set is big enough. All the algorithms with lower algorithmic complexity almost completely disappear. Now, what's the problem with that? The problem is that loops with algorithm complexity, which are O of n log n square, and to the power of 3, scale badly. So if the dataset size increases from n to 2n, the algorithm with complexity of O of n square will have to execute 4 times more work. So the dataset increases by 2, but the amount of work increases by 4. So if you have a program that processes large data set and you have algorithms with high algorithmic complexity, then this will not work on regular desktop systems. In that case, you will need to use some kind of massively parallel architecture, such as GPUs, accelerators, or high performance computing systems with many cores. Okay, the next problem that causes the programs to become slower more than expected is related to memory allocations. So system allocator, which is an implementation of malloc and free or new and delete, is a shared resource between all the components in a single process. So it's a shared resource. So we have, with regards to the memory allocation, there is a possibility of oversubscription, but this is not the talk, what this talk is about. So if one component is heavy on the system allocator use, this affects other components as well. Why? There are several reasons. One is that it increases memory fragmentation. Memory fragmentation, I don't know if you remember it, but increase in memory fragmentation means slower memory allocations. So the malloc and free will run slower. It also increases the data cache miss rate. So you have more data cache miss rates. More data cache miss rates is connected to slower programs. Codes that are heavy on the system allocators, that make a lot of calls to malloc and free, are especially vulnerable to this. So indeed, if this is the case with your program, then you need to pay attention. Now, the codes that typically have this problem have a lot of calls to new, delete, malloc free, and also if you're using data structures that behind the scenes make a lot of calls to new, delete, or malloc free, such as tree and hash map based containers, such as std set, std unordered set, std map, std list, and so on. So this can create a problem of memory allocation, memory fragmentation, and generally the slowdown that comes with it. Okay, so next topic is our compiler optimization. Sorry. So what's the problem with compiler optimizations? So modern software performance really relies on the compiler. So in order to get the good performance, the compiler needs to be able to do its job. Now, the compilers internally use pattern matching and heuristics to generate optimal code. What this means is that compiler optimizations can break easily if new code is added. You can add a new code, something really simple and not expecting, and you see like a drop in performance by 2, by 3. Also, sometimes breaks in performance happen when you change the compiler versions or when you change compilers. So the example one where this happens is vectorization. So vectorization is optimization that speeds up your software, and it's part of the compiler. It works by, instead of processing one data at a time, it can process like 4 or 8 data by using special vector instructions of the CPU. Now what happens is there is a loop, and the compiler can automatically vectorize it, but at some point you only change one little thing in the loop and it breaks the vectorizer, and from that point on your code reverts to the scalar version of the loop, which is several times slower. A second example is an inlining. So inlining is compiler optimization when you take, instead of calling a function, you take the function body and copy it in the place of the call. Now this has several benefits. One of the benefits is that it removes that it removes the call, so the overhead of call disappears. But another more important benefit is that when you do inlining, you enable additional vectorization, additional optimization for the compiler. Now, what happens? You have a function with the compiler inlined, and then you add 1 or 2 new lines, and the compiler says, "Okay, this function is too big. I'm not going to inline it anymore." And when this happens, the performance of the code can drop significantly. Now, what is the solution to this? Is writing simple, easy to understand code on the hot path is the way to go. So hot path is the path your program is executing, the most important lines that get executed the most. So most compilers are optimized for simple, easy to understand code. You should avoid everything that's not needed. You should move it outside of the hot path. Okay, moving on. Next are the hardware issues. So the hardware issues also make your program more slower than it actually needs to be. So as the software evolves and becomes bigger and bigger, it also becomes less and less hardware efficient. What does that mean? Is more instruction cache misses and more data cache misses. Okay, let's talk about them a bit. So if you have a bigger program, it has more instruction cache misses. So what is the instruction cache? So instruction cache is a small cache memory inside the CPU that is used to speed up fetching of instructions from the main memory. So fetching of instructions from the main memory is very slow, so the CPUs have this instruction cache. Now, if the instruction is in the instruction cache, it can be executed quickly. Otherwise, the CPU needs to wait for it to be fetched from the main memory. The bigger the program, that results in more instruction cache misses. Now, typically, when the program size increases by 2, the program gets 1 to 2% slower. Now, the programs that often switch between short functions. So there is this instruction, the program is running a little bit this function, then moves to another function, then to a third function, then to a fourth function. Those kind of programs typically exhibit more instruction cache misses. Now, there are a few ways how to solve this. One is the tools that are called, one tool that can solve this is called Bolt, and the other one compilers profile guided optimization. So what is the idea there is that your program, you record the runtime behavior of your program, and then the compiler or Bolt reorganizes that program to minimize the number of jumps. Another way to do it, it's not listed here, is to use huge pages on instruction. Oh, sorry. Don't use huge pages, it's another story. Sometimes compiling for size, and this is the option O of S, can also help. Okay, next. So when bigger workload or bigger data set results in more data cache misses. So data cache is a small memory inside the CPU that you can use to speed up access to commonly used data. So this is really common and used everywhere. So if a piece of data is in the data cache, the access to it is fast, otherwise it is slow. Now what happens is that the performance of programs with hash maps, trees, linked lists depends a lot on the data structure size. So smaller data structures better fit the data caches, and since they do, access to them is faster. Now, for example, if you have a small hash and you perform 1 million lookups in the small hash map, it will be much faster than performing 1 million lookups into the large hash map, even though the amount of executed instructions is completely the same. Now the reason why this is so is because of the data cache misses. So here's an example. We perform 8 million searches in the hash map. Now the performance, you'll see here that the runtime is in seconds, and here's the hash map size, and you see that the runtimes are really short for smaller, but then when the hash map grows above some size, so this is 64k entries, it will start growing a lot, and again when it grows over 4 million entries, it will start growing a lot again, and so on. So these performance drops are related to L1, L2, L3 and TLB caches, because those caches become too small to accommodate the whole data structure. So one of the ways that data structure developers fight this is they try to minimize the size of the data structure in order to decrease the number of cache misses. Now, one more important thing is if you have your program uses classes extensively, and larger classes means again more data cache misses. So every time you add a new member in the class, this decreases the performance of processing that class. So what's the reason for that? So the reason is that the data is fetched in blocks of 64 bytes from the main memory. Now, if your program is not accessing the whole block, most of those transfer bytes are wasted. So your CPU is fetching some data, but you're only using some part of it, not all. And this is what happens with the large classes. So you're bringing in new members that in the hot code, most of those members will not be accessed, and this makes it slower. If you have a hot loop that is not accessing all the members of the class, consider moving unused members to auxiliary classes. So this is the way how you should typically solve it. So here we have an example. The time needed to process 20 million elements of an array. And here we have a class size in bytes going from 20 to 504. And then, but here we have the runtime in milliseconds. And you see for the smaller class, the runtime is about 20 milliseconds. But as the class size grows, it goes to about 140 milliseconds. Now, the same instructions are doing the processing. Nothing is changed, but the slowdown is quite visible. So in this case, it's a few times, 5 times. The slowdown is 5 times. Okay, so I try to cover here all the things that typically can make your program slower over time as you add new features and as you or the data set size increases. So you've seen that these degradation in performance are expected as the software complexity grows. The more complex the software, the less efficient it becomes in many ways. Also, the bigger the data set, it's also less efficient to process it. However, not all is lost. As explained, there are many techniques to keep performance degradation controlled. So I explained some of the techniques. You can find some of them additional on my blog. So feel free to visit. I have a site, https://johnnysoftwarelab.com, Twitter account if you use Twitter, or LinkedIn if you use LinkedIn. Since I'm doing performance consulting, in case you have a performance problem in your software, feel free to contact me. So my email address is this. Thank you very much.
Maybe I'll start with the first one. Thank you for the very insightful talk. I think you covered a number of different reasons why we could lose performance over time. Within your experience, are the root causes fairly even, or is there a particular class of problems that you see as the most common pitfall that affects the software in production?
So it will be really difficult to say because it really depends on the project. Some projects are more prone to one type of problems, other projects are more prone to other types of problems. For example, in HPC world, you will see often these problems with data cache misses because when the data set grows. But for example, I think in the microservice world where you have many components that are in separate processes, and when they communicate over network, then you see these architectural issues that actually appear. So there is no one answer.
Can I go with a question?
Sure.
So I wonder, when we operate at a large scale, it's sometimes very hard to keep an eye on all these aspects of performance. So I wonder if you have any recommendations for the tools to use to automatically identify and flag these regressions as they appear, instead of waiting for things to regress to such a point where we absolutely have to fix them.
So this is more related to performance testing and performance. Let's say you're ensuring there are no performance regressions, and this is something. This topic is completely something completely different. So normally, if you want to make sure there are no performance regressions, you need to set up some kind of performance testing as part of your continuous integration system. Now, this is not simple, because sometimes, because of noise, you might appear that you have a regression when you actually don't, or other way around. So it's not easy. The second problem is, as far as I know, there are no automatic tools that can help you with this. And it's not only that you want to measure performance, you want to measure memory consumption. You don't want the memory consumption of your program to explode, especially if you're delivering your code to many users. So these are all things that are, let's say, interesting. Now, when it comes to tools used to detect performance problems, there isn't anything that there are tools that you can use in if as a developer, so you're debugging a performance issue, and then you use a certain tools to make sure to check for hardware efficiency, to check for example, if there are some problems with the operating system. For example, you're asking too much memory from the operating system. Earlier, there used to be a tool called performance sanitizer, something like that, but it was a tool that at runtime collects some data about performance and tell you if you're doing something inefficiently. But I think that tool is now obsolete. It's not maintained anymore. So yeah, so that's the answer.
There are two questions in the Q&A. The first one is, in a complex and large program, how do I make sure which is in the hot path?
So if you want to figure out what is the hot path, first thing you need to know, to have an example of a typical way your system is being used. So for some systems that can be really difficult to have a typical way, because, for example, imagine a web browser. So the web browser can be used in many different ways. Now you need to have that, and then there are these tools called profilers. They're really profilers are very similar to debuggers. So a profiler will run when you run your program under a profiler, similar to when you run it under a debugger. The profiler will collect the information about which function was executed, what amount of time, and then at the end of the execution, it will give you a report, and then you will see which function takes the most time. And actually, if you're doing your first time on a project and you're not familiar with the code base, it is a worth thing to run the code through a profiler and see which are the hot functions, and have a look at code of the hot functions, not everything. So it will drastically limit the amount of code you need to investigate. So profilers are the way to go to see which code is the hot code.
Thank you. The second question, how do you tackle solving a problem with a big map set? Is it to try and split it into smaller submaps and do batch processing on them? How would you split up your data set into batches?
So if you have a STD map, so I'm assuming that the question is about STD maps or hash maps in general. So the problem with the hash map is every time you calculate the hash and then you go to the bucket corresponding to that hash, you will, if the hash map is large enough, you will have a hash map miss. Now there are a few ways how to work around it, but actually there is no way, with regards to hash map, there is no way to make it, let's say, fast as accessing an array sequentially. So what if you have a really large hash map, you will want to enable huge pages in your operating system and allocate the hash map from the huge pages, because this can bring you a performance improvement about 2 times if the hash map is large enough. So this is one simple trick that you can do. Second thing that you can do is use different implementation of hash maps. So normally there are 2 types of hash maps. One is open addressing hash maps, and the other one is they're called. Does anybody remember? I cannot remember the name.
You mean like Bloom filters or something like some randomized data structures?
No, there is two. One is the open addressing, and one is
Chaining.
and chaining. Yeah, chaining and open addressing. Yes. So chaining is when you have a collision in a hash map, then you allocate a linked list for all the values in the bucket. And the open addressing is when you have a collision in this bucket, you move to the next bucket. Now these hash maps with open addressing, so when you are just moving to the next bucket, are generally more data cache friendly, and also they offer higher instruction level parallelism. So they're often used. If you have a hash map, there are many implementation of really fast hash map, and I suggest that you look them up on the internet. There was a really nice article where the guy was comparing 6 or 7 implementation of hash maps.
By the way, I just want to add one more thing. Like, for example, there are the hash maps like F14 from former Facebook, which uses SIMD instructions to also perform really fast comparisons of the hash keys. And also there are interesting hybrid data structures that use a bunch of buckets. So instead of just having one entry for open addressing, you can have, let's say, 4 buckets for each cell. So this way you can combine SIMD instructions, and also in case you have conflicts, you don't necessarily have to use complex strategies like Robin Hood hashing or cocoon nesting hashing and other approaches that are much more complex than linear probing, let's say.
Yes.
There's one more question from William. How do you isolate cache misses as a contributor to the performance versus other low-level contributors, such as context switching between threads? What would your process be for identifying these issues before forming a solution?
So can you please reread the question? Because
sure, yeah. The question is, how do you isolate cache misses as a contributor to performance versus other low-level contributors such as context switching between threads? So I guess the question is, how do you identify, is it cache misses or is it context switching or some other low-level contributors? How do you sort of hone in on those? And then what is your process for identifying the root cause before arriving at a solution to fix those?
So if you're running on an Intel platform, so you have an Intel CPU. Intel has delivered an Intel vTune profiler. It is the best tool that exists, and I think it's the only one that exists for profiling application for hardware efficiency. So what happens is that this tool will run your program, and when it's done, it will tell you how much cycles did your program spend and how much cycles were wasted because of different things. And then it will draw out a diagram, and in diagram you'll get the percentages. For example, it will tell you 35% of the spend time was spent because waiting from the data from the memory to waiting for the data to the memory, and 5% for spend because there was not enough division unit resource on the CPU. Now, if you use this Intel vTune, and this part of the vTune is called microarchitectural analysis, it will tell you this information about the hardware efficiency, and then you just solve the issue by you look what are the things, what are the parts of the, what kind of inefficiencies waste most of the slots of the cycles, and then you just focus your attention there.
If there are no other questions, I guess I'll ask another one. So now a lot of the workloads are running on cloud providers where you have a very large variety of underlying CPU instances and families. One of the issues that that happens at scale is you might run into a bad processor that on the face of it seems to be just fine. It doesn't trigger any errors or anything, but it's silently either slow or corrupting data. Have you come across any such instances, and how do you go about like root causing this in an environment where you are not in full control of where your application eventually runs?
So normally I don't work on cloud environments, so I cannot give you the exact information. I can, let's say, extrapolate. So with information I know. So we have different types of CPU. Profiling in the cloud system is difficult because on many systems the performance counters are not even available. So you don't have good tools to profile there. If you can create an environment on your local system, for example, if you're debugging an environment in your own environment, and then you see there is a problem there is a problem with hardware efficiency in your own environment, then you can actually try to fix your program or application. Now, when you're running on the cloud, you're not sure exactly what happens. If you know that locally you have no problems, but in the cloud you do have problems, so you should probably pay attention more to the system details, like CPU frequency, CPU load. There are tools to measure the amount. Sometimes the system is slow. It's not because the CPU is 100% used, but because the memory controller is 100% used. So you have a contention on the memory bus, not in the CPU. So CPU seems to be idle, but it's enough. If you have 48 cores, it's enough. 4 cores can create a lot of traffic if they're really memory intensive. So you want to take you take account of that, and also to take account of the power consumption in the system. So these are things that you should in principle be able to measure in the cloud system. And finally, one important thing that you also want to mention is there is this cycles per instruction metric. So how many cycles is needed to execute one instruction? And if you're running on a cloud system, that cycle per instruction should be similar to the one you're getting on your system. If they're similar, that's fine. But if you see a large difference, especially if this cycle per instruction is larger on the cloud system, then you have something which is not easily explained, some problems that is not quite clear, and can suggest a problem of the misconfiguration, some other processes running in the background, different compilers, something like that.
Okay, I think that's all the questions here. Thank you, Ivica.
Thank you.